Hi, and welcome to the Calculus 1 video tutor. The purpose of this DVD course is to teach you about calculus, obviously. And the way we're going to do that is we're going to work a lot of example problems in each and every section. Before we go into that stuff, I just want to give you my 2-minute speech on calculus and why it's important. The first thing I really want to say is, first of all, put all of your fears aside. Okay, calculus has this bad reputation as something really hard to understand, something really complicated because, geez, they named it calculus. I mean, calculus just sounds mean, okay? So I want you to take those thoughts, I want you to put them on the back burner because they're not true. I'm going to teach you how to do calculus, and it's going to seem like third grade math. That's my goal, okay? My goal is to work every step, step by step by step, and to do enough problems so that you feel comfortable doing them on your own. And the goal is that getting that experience will help you go into your homework and into your tests and do well right off the bat. Now, the other thing I wanted to say is that I'm not going to work problems of every type. I'm not going to cover every single topic that you might cover in class. So what you're going to need to be willing to do on your end is to pick up the book and to work additional problems. I promise you, I've tutored a lot of people in this subject and in other subjects in math. And really, the way you do it is just like football or hockey or soccer. You have to practice it, okay? So I'll do my part. I will teach you I won't say the shortcuts, but the quick and the straight truth on how to do the problems. I'm not going to have a lot of theory. I'm going to explain what I need to explain to you. Mainly, I'm going to show you how to do it by working examples. So watch the DVD course from beginning to end, and I promise you that if you do that, and if you make sure you understand what I'm talking about before I go on, then we will be in good shape. Okay, so let's move into the topic of this particular section of the class, the first section, which is the concept of a derivative. Okay, there are two main things that you're going to have to learn in Calculus 1 if you have to just boil them down. The first one is called a derivative, and we're going to devote the next several sections to that. And then the second topic really is called an integral. And they have goofy, really scary sounding names, okay? But instead of just telling you what a derivative is, I want to show you what a derivative is. So let me try to do that. Let's say this pen here, okay, is moving along at a constant speed like this. It's not speeding up, you know, it's not slowing down. It's just marching across your field of view like this at a constant speed, okay? So if it were doing this, okay, and if you were in your car and it were going along like this, then you would say it would be going at like, I don't know, 10 miles an hour constantly. The needle's at 10 miles an hour, okay? So it goes across constant like this. So if we were to plot the position of this pen as a function of time, what would it look like? If we did that, we would have a graph like this, and this would be time, and this would be position. I'm going to say POS for position, okay? And then along this axis, you would have little tick marks for time, 1 second, 2 seconds, 3 seconds, 4 seconds, so on. And then on this axis, you would have, you know, your distance, you know, how far away have you gone from the origin? Okay, so this could be like 1 feet, you know, 1 foot, 2 foot, 3 foot, and so on. So if this pen is going along your field of view at a constant rate, what would this graph look like? I think you could convince yourself that this graph is going to look like a straight line, because each unit of time that I go forward, it goes forward in position. Every time I go 1 second, it goes up the same amount in position. So as I go forward in time, it goes forward in position by the same increment. Each time I go 1 second, it goes up a certain amount each and every time. Okay? Something that would accelerate, if I were to accelerate this in front of you, then it might look something like this, because as I go forward in time, it might just scoot on by faster than you can really keep up with it. But that's not what I'm really after here. So this is called the graph of this pen as it goes across your field of view at a constant velocity. So then if you were to write this as an equation, you might have the position as a function of time would equal, and I'm just going to say in words here, a straight line. Okay, obviously a straight line. Okay, and in equation terms, that's just m, which would be the slope of the line, times time. If you go back and remember from your algebra, the formula for a line in the most basic sense is just some slope times a time. And it goes through the origin here, so there's no there's no y-intercept. The y-intercept 0, so it's just p is equal to mt, where m is just a slope. It's a number, 1, 2, 3, 4. It's just a slope. Okay? Now, if I asked you the question, okay, this is a graph of the position of this as a function of time as it goes across your field of view, then how could you plot the velocity, or the speed is another way to say this, of this pin that goes across your field of view? How would you do that? Well, I already told you, and when I set this up to kind of explain this to you, that this pin is moving along your field of view at a constant speed. I already told you that, so I kind of already gave you the answer. The answer is, well, it's moving across your field of view at a constant speed, and so if it's moving across your field of view at a constant speed, the velocity must be a constant. In other words, as I march forward in time, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, as I march forward in time, the velocity does not change. It's constant. It's constant, in this case, at 3 meters per second or something like this, or whatever speed you want to represent. If it's going faster, well, then the line will be up here, and if it's going slower, well, then the line will be down here. But in this case, I just picked a number. Okay? If you were to write this as an equation, the velocity as a function of time, you would say the velocity as a function of time is constant, because I just told you that. Plus, it looks like it's constant, isn't it? Okay? And then finally, we're going to draw one more quick graph here. As a function of time, what is the acceleration of this pin that goes across your field of view? Well, I think you can convince yourself that since it's going across your field of view at a constant velocity, I've kind of, again, also already told you implicitly it's not accelerating. Acceleration is when you speed up or you slow down. But when you go straight across at a constant velocity, the acceleration is 0. So the acceleration as a function of time is going to be right here at 0. And it's going to be hard to see with all this black ink everywhere, but it's right here along the axis. All right. So we have a pin that goes across your field of view at a constant velocity. Its position is going forward at a constant rate per unit time. Its velocity is a constant because it's not speeding up or slowing down. And again, because it's not speeding up or slowing down, its acceleration is a flat 0 because this is 0 down here. And if we had to write this as a function, we would say the acceleration as a function of time equals, can you guess what? The big fat 0, because there is no acceleration for this problem that I'm giving you here. All right. Now, you'll be surprised, probably, if I tell you that we just took 2 derivatives on the board in not an equation form, or not rigorously with a bunch of equations, but I have already explained to you what derivative was. I just didn't tell you it was a derivative, okay? Big picture is, and you're going to have to remember this, but it's not going to be hard to remember, the derivative of something is just the slope of it, okay? Or you could say, the calculus books like to say, it's the rate of change, okay? So if you look at this graph here, okay, the position graph, when you take the derivative of the position, you get the velocity. When you take the derivative of the velocity, you get the acceleration. So these are 2 derivatives. We've taken a derivative here, and we then arrived at this. So the velocity is the derivative of the position. And when you take the derivative of the velocity, you get the acceleration. So all this derivative business, what does it really mean? I'll say it one more time. The derivative is the slope of your curve, okay? In this case, it's not really a curve, it's just a line. So the line has a fixed constant slope. Think about it from algebra. The equation of a line is m times t, where m is the slope and m is constant. So here, m is a constant. The slope of this curve is a constant. So when we take the derivative of the position and get the velocity, the slope of this curve is what we're saying is a derivative, and the slope is a constant, so it's a constant here. The velocity is the derivative, which is the slope of this, and since the slope is a constant, the velocity is a constant. Okay? Now let's look at this. Again, the derivative of a curve or a function or anything like this is the slope of the curve. In this case, this is a flat line, okay? What's the slope of this line? Well, it's flat, okay? You should remember from your algebra that the slope of this is just 0. There is no slope. Slope increases as you go up with your lines like this. Eventually your slope gets to infinity if you go straight up and down because it's infinitely steep, okay? But when you're flat like this, it's like going up a mountaintop. You see, you go up the mountain, this is real gradual slope, almost 0. You see, I live in Houston, the slope is 0 around here. There's really no hills, but when you get to Colorado, you go up the mountains, the slope gets higher, okay? So here, the slope of this is 0. So the derivative of velocity, in this case this curve, which is the acceleration, is 0. And it's 0 for all values of time because the slope of this is 0 for all values of time. And this is a constant because the slope of this is a fixed constant for all values of time. Okay? So, I want to go ahead and formalize a few of these things that we've just talked about. Not really so much formalize it, but just sort of write it down a little bit so you can see what the heck I'm talking about in words or in equations. Okay? The slope of the position function, which is this guy, is the velocity function. That is a fact. That is just calculus 101, basic fact. The slope of the position is the velocity. Okay? The slope of the velocity is the acceleration. That is a fact, a universal law of nature. That is calculus 101, basic physics, basic calculus. And just to beat it into your head, just so that you are with me here, the slope of a curve is what we call a derivative. All right, you have successfully tackled in a conceptual way what we're going to spend the first half of Calculus 1 on. Okay, in your class, you're going to learn about derivatives for about a month and a half, or maybe almost 2 months, and you're going to learn about integrals. That is what a derivative is. From here on out, we're going to talk about some mumbo jumbo, and I'm going to show you how to take derivatives of more complicated functions than just lines. Okay, and they're going to become second nature after a while. And I'm going to teach you how to do that, hopefully without too much pain. Before we do that, I want to go ahead and just give you a little bit of a flavor for something that's not quite so simple. So before we jump into a bunch of equations, I'm going to give you another example, kind of like that one that we just did just a second ago, except it's not going to be quite so simple. And the point of them is that you'll be able to compare the two examples that we just did together. Okay. So what if we have a pen that goes across your field of view and it accelerates as it goes across? So it's speeding up. You see it starts out slow and then it speeds up like this. Well, if we were to draw the position, P of t, I'm going to call this the position, as a function of time, what would that look like? Well, as you start off in time, it's going a certain speed, then it's getting faster and faster and faster and faster, and then it goes like this. Well, your position, as you get farther in time, is going to go rapidly up because I'm speeding up. So it's going to look like this. So for this particular example, I'm going to say P of t equals t squared. Okay, remember the equation of a parabola kind of looks like this curve like this. So I'm just going to say that this position function is a parabola, which is given by this equation here. Okay, now you might look at me and say, okay, smart guy, how are you going to take the derivative of this function when it's not a line? Okay, I mean, I already told you the derivative is the slope of the curve, okay? But this curve is changing. So what slope do you use? I mean, what do you do here? Well, when you think about it, here near the origin, the slope is very shallow because I'm just starting out, because I'm just starting to speed up, okay? And as I go up the curve, the slope of this curve gets steeper and steeper and steeper, eventually gets real steep as I get up there. So that's why I chose to do this problem, because it is a little bit more thought-provoking. What I really want to show you is that the slope of this curve, let me back up and just say, not the slope of the curve, the slope of the line tangent to the curve here is pretty shallow. Okay? The slope of a line tangent to the curve here looks more like this. And then if I'm going to go up here, the slope of the line just barely touching the curve there looks something like that. So when I say the slope of a line tangent, I mean a line that barely touches in one point. Okay? That's how you would look at the slope. So obviously the slope is changing as you go up the curve because you're speeding up. Okay? That's why this problem is a little bit more challenging than the one before. So then I ask you, what would the velocity look like? Same thing we did last time, v of t. Velocity is a function of time. Okay? Well, I already told you that it was speeding up, right? So the velocity must be increasing as I go up in time. Okay? That means when I start out here, I have a certain velocity, and it's getting bigger and bigger and bigger, and I'm speeding up, and I'm speeding up, and that's why my velocity is going up, 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 up. This would be like sitting in your car and constantly pressing on the gas pedal down, 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 down. You start 10 miles an hour, 20 miles an hour, 30 miles an hour, 40 miles an hour. What are you doing? You're accelerating. That's what you're doing. So your speed is going up. Okay? So the derivative of the position, again, gives you the velocity. In this case, your slope here, which is the slope of the tangent line to the curve, is very low. So your velocity is low because the slope of this line tangent to the curve is the derivative of this, and the derivative of this is velocity. As you march up the curve, your slope gets bigger. So the derivative gets bigger, and your velocity is bigger. The slope of this little guy tangent to the line here, to the curve here is bigger still. And since the slope of the line tangent is the derivative, and the derivative is the velocity, velocity goes up. So as the slope goes up, velocity goes up. And so you've taken a derivative there in graphical means. So if you're going to write it down, then you could say v of t is 2 times t, let's say. Okay. In fact, this is the exact derivative here, but I haven't shown you how to calculate it in terms of functions yet, but this is the derivative of t squared is 2t, and this is a line with a certain slope. Okay, so it describes this equation right here. Now, I ask you, what is the acceleration? A of t. Well, we already said that in the initial problem statement that you're speeding up, right? So we know that we're accelerating. So then you have to ask yourself, the derivative of the velocity is the acceleration. That's another way of saying, what is the slope of this curve? Well, the slope is constant. The slope did not change. Unlike this, the slope is constant because this is a straight line. So I'm going to go up here to 2, okay? And I'm going to draw a line here, a constant slope, which is a constant acceleration. So that means as I move forward, my acceleration, I'm accelerating at a constant speed, like this could be accelerating at 2 meters per second squared or something like that, a constant acceleration. I'm constantly increasing my velocity by the same amount each time that I go forward in time. Okay? So this is the acceleration would be a constant. In this case, it's equal to 2, and so you have constant acceleration. So you have gotten an introduction, a basic introduction to derivatives. The big picture to remember here is derivative of something is just the slope of the line tangent to the curve. You know, if it's just a line, it's just the slope. If you have something curvy, well then at each point there's going to be a line tangent to that curve, and the slope of that line is called the derivative. It just so happens that position, velocity, and acceleration are just really familiar things for us to talk about because you all drive in your cars and you know what those terms mean. But you could take the derivative of any function at all. The function could be describing the pressure change in a vessel. It could describe the trajectory of a spacecraft, anything like this. Okay, any function you write down, you can take the derivative of it. When you do that, you're taking the slope. You're looking at the slope. You're looking at how does that line change, or how does that curve change with respect to time or with respect to something else that you might be looking at. Okay, cool. Let's go forward, and let's make this a little bit more concrete in terms of what your book is going to actually tell you. I'm just going to write some stuff down here that I want you to remember. The derivative is by definition equal to the slope of the line tangent to the curve at a point, okay, at a given point. So the slope could change as you go up, and then your derivative would change, okay? So in order to, I'm going to teach you a little bit of the way that you write this down. I'm going to show you the symbols in calculus that we use to talk about derivatives. Remember we said that velocity was the derivative of the position? Well, you write that like this. The velocity, okay, is equal to p prime of t. Remember, p of t is the position. When you put this prime here, this means derivative, okay? So you have the position function, you take the derivative of it, which is the rate of change, the slope of that tangent line, and what you get back is called the velocity. Another way to write this, these are exactly equivalent ways to write it, is the derivative of p of t with respect to t. So you would say in words dp dt. Here you would say p prime of t. In either case, you're saying the same thing. What you're saying is, give me the slope of whatever function I'm talking about, p of t, a of t, u of t, it doesn't matter. So in this case, you're taking the derivative of p with respect to time, because time is the independent variable there. And so this is the terminology here. P prime of t, dp dt. You'll see both of them in your books. They mean the same thing. They're just different ways to write it. And similarly, the acceleration as a function of time is equal to v prime of t. You take the derivative of the velocity, that's what this prime means, and you get back the acceleration. And in order to write it in this way, you would say d v dt. Okay? So the derivative of the velocity is equal to the acceleration. Now, I'm going to show you something that might confuse you a little bit, but I promise you that I'll make it clear. This is also equal to p double prime of t. Do you have any idea what that might mean? Okay, well, one little prime means first derivative. It means I give you a function, take the derivative of it, which means take a look at the slope, and then you'll get a function back, and that will be called the derivative. When you have two little marks here, that means do the derivative 2 times. So take one derivative, and you get some function back, and then you take the derivative again, you look at the slope again, so 2 times total, and you get that. So if you remember, we had our position graph, I'll put POS, our velocity graph, and then our acceleration graph. And I said this was velocity was the derivative of position, and then acceleration was the derivative of velocity. So that's what we're writing here. Well, if you start with position and you go, here's the first derivative, here's the second derivative, well, you arrive at the acceleration. So what we're saying is the acceleration is the second derivative of the position. 1, 2. It's really not rocket science. First derivative is velocity. Second derivative of the position is the acceleration. So the other way to write this, in terms of that d business here, is d squared v dt squared. It's just notation. I'm just trying to teach you notation. Here what you're saying is I've taken the second derivative of the, oh, I have a typo here. The second derivative of the position with respect to time, and that's equal to the acceleration. Okay, so it's just notation. Okay? Now, the next thing I want to really say, though, is that just to kind of point things out and make things clear, let's say you have some random curve. Ooh, looks kind of crazy. And then here, there's some sharp point or something, okay? Well, clearly, if I want to look at the slope of this curve as I go along, here would be like the slope here, so the derivative would be whatever the value of the slope is, which is a positive value. If I'm looking at this in this instant, the slope looks something like this, the slope of the line tangent to this curve, which is a negative slope because it's going the other way, right? So that's another value of slope. And so at every point, you've got a value of the slope based on the line tangent to this curve, okay? So it's changing constantly as you go up and down, the slope is changing. At this point, you have a cusp. The derivative is not defined here. The derivative not defined. Basically, the rule of thumb, the thing you really need to remember is in order to take the derivative, you need to have a smooth function. You can't have a discontinuity or a sharp point or anything like that, or a step function. You have to have a smooth curve in order to take a look at that line tangent to it. Because when you think about it, how would you draw the line? I mean, you got a single point here. Would it be here? Would it be here? I don't know. So you can't really do that.